Welcome to part 3 of the video series Getting Started Reinforced Concrete Building Design with Revit. Let's begin with a quick recap. In part 1, the physical model was constructed. Part 2 introduced the analytical model, which was quickly derived using the analytical model generator. After generating the analytical model, support conditions, load cases, and loads were added. This part focuses on transferring data from Revit to the structural analysis software using SOFiSTiK analysis and design. The analytical model will be enriched with additional information required for finite element analysis. This step includes mapping Revit materials and loads to their SOFiSTiK counterparts, and positioning all components to ensure consistent identification from the BIM model to the FEM model. Our process begins where the previous session ended. The analytical model is created, aligned, and includes defined loads and support conditions. Work now continues in the SOFiSTiK Analysis tab, where the handover to the FEM model takes place. The first step is to select the main system, which is essentially any 3D Revit view assigned for structural analysis and serves as a central working view. The previously created 3D AMG view is pre-selected and confirmed. In the Project Settings dialog, we need to assign a design code. We choose the generic Eurocode with no national annex. Once defined, the command acts as an anchor point for returning to the main system view. A quick look at the analysis browser, found in the top right under Manage, reveals a simplified project browser focused solely on structural analysis. While useful for managing calculations and subsystems, it is not required for this single system project. So we will close it again for now. Next is the mapping process, which aligns Revit materials, sections, and loads with their SOFiSTiK equivalents. Only objects used on visible elements in the active view will be listed in these dialogs. Materials. The leftmost column shows the Revit material. In our case, the cast-in-place concrete we used for all physical elements that has been transferred to the analytical elements. Each unique material will show up on its own row. The middle column names the physical asset assigned in these materials. Each material asset will be mapped to a SOFiSTiK material based on specific material properties, for example, the compression strength of the concrete. For reinforced concrete materials, it is possible to find a SOFiSTiK material for concrete and reinforcement independently. This mapping is an automatic proposal by SOFiSTiK Analysis and Design and can be manipulated down to every single material property relevant for FE analysis. Sections. The current view includes 4 distinct combinations of sections and materials. The element type is also listed. Each row is mapped to a SOFiSTiK cross-section, which combines the section and material information. The mapping is automatically assigned and can be edited if needed. Loads. The previously defined Revit load natures are now mapped to SOFiSTiK action types. This enables the SOFiSTiK Action Manager to apply partial safety and combination factors correctly. Let's talk about SOFiSTiK structural properties. These are extended properties relevant for structural analysis that Revit elements otherwise do not have. To control them, we activate the side panel through the ribbon command. When selecting an analytical or its linked physical element, its structural properties are shown. Without any selection, the system view settings are displayed, which I will explain later on. The next step involves assigning group numbers to components. These are useful for targeted design tasks, for example, differentiating between slab types with varying crack width or concrete cover requirements. The following scheme is applied. Horizontal elements, namely beams and slabs, receive group numbers like 10, 20, or 30. Vertical elements, like columns and walls, receive group numbers 15, 25, and so on. Assigning SOFiSTiK names allows to identify members in the documentation. This is also possible thanks to the SOFiSTiK structural properties. Let's mark this column with a C, give it a unique number, and add information about its location in terms of grid location and level. To save time and reduce errors, the command setNames is used for automatic naming instead of manual entries. After selecting all components and clicking Finish, we see a dialog pop up that groups all elements by type. For columns, the before-mentioned naming rule is applied. We can use the drag-and-drop method to rearrange the order of named components, or switch to the edit mode and use the syntax explained below. We define a prefix, C for column, followed by a sequential number, and put the grid location and top level in parentheses. These rules are highly customizable, and the preview shows the applied names at once. Once confirmed, the names are visible throughout the structural analysis and its documentation. In addition, let's also create a plan using the nameView command from the SOFiSTiK Analysis ribbon tab. For this to work, the SOFiSTiK name property needs to be mapped to a shared parameter, so we confirm with yes. Let's create a plan showing all columns on level 3. By default, beams are modeled as centered in the slab plane, which is perfectly fine for an initial analysis. Later on, the effective slab width can be activated. Setting this to any value other than 0, for example 1 meter, enables SOFiSTiK's T-beam logic, which adjusts the stiffness accordingly for more accurate results. Revit itself does not provide any possibility to find the connections between analytical panels, and assumes them to be 100% stiff. Using the edge release command, we can model, for example, hinged conditions. In this example, we want the walls on the top floor to be connected to the floor slab with rotational freedom but fixed translations. The affected edges are color-coded during the command, and the settings can be reviewed in the structural properties. Before exporting to SOFiSTiK, the System View page in the Structural Properties is revisited. Under General, we see Self-Weight Load Case is defined as DL1, and the following analysis tasks are confirmed. Generation of the FE model is turned on, as well as the application of loads. We have the analysis of load cases turned off, as this is handled later on. After the calculation is completed, we can look at the report and visualize the FE model. The mesh, edge releases, and T-beams appear correctly. In analysis and design, we abide by one important principle. What you see is what you get. This means only visible analytical elements in the Revit view are exported to SOFiSTiK. To demonstrate this, a few columns are hidden. In addition, we also want to increase the mesh refinement to 75%. After recalculating, the hidden columns are no longer present in the exported model. Let's reveal the columns again and rerun the analysis once more. With this, the model is ready for export to SOFiSTiK for structural design. The next part of the series will focus on the design of the load-bearing systems. Stay tuned.